So I'm going to give you start with a kind of an overview of neural networks and their history, which is actually somewhat more exciting than you might imagine. And then I'll sort of home in on how we study the brain through the lenses of different scales of networks, both at the molecular and at the connectomic level. And then I'll try and wrap up with something suitably exciting, talking about AI and the usual stuff that people like to hear about these days. Okay, so this is the overview of what I'll be talking about. So here's a very, very, very short history of the question of how one understands thought. So formal reasoning has been around since long before the Christian era, more than 2,000 years in the Indian writings, in ancient Greek writings. It's been in Chinese even. It's been there for a very long time. This is not new. The idea of trying to systematize this started in the 1600s, and then Hilbert had this extraordinarily ambitious program, I'm sure some of you know about this, to formalize all of maths on a strong axiomatic foundation. And this ran into some slight problems. That is, Gödel and Turing, both in approaching the problem from completely different ways, showed that it could not be done, that there are fundamental limitations to how you can systematize formal reasoning. Turing, the way Turing approached it was through the Turing machine, which was the sort of one of the precursors for the modern computer. In other words, a system by which you can tell, in a very formal way, you can tell a machine to carry out a series of instructions which can perform logical, mathematical operations. And this became what we call computation, and that's the universal Turing machine, which is basically the statement that all computation is equivalent. It doesn't matter whether it's happening in my wristwatch or on the biggest computer on the planet. Fundamentally, they're doing the same thing. If you have enough time and enough memory, you can run the same computation on my wristwatch as you can run on the gigantic computer. So this is actually a very profound statement, because it makes the question of computation a level one. And it's also very profound because if, like me, you believe that the brain is a physical object, therefore all the computations that the brain does are equivalent to what your wristwatch can do. Yeah? And if you take the further philosophical leap to think that intelligence and cognition are computational operations, then it means that, take the leap, it means that you can do all of these quote unquote high level cognition things on a computer. Anyway, you've seen where that's going. Now let's get to the modern stuff. So, so programmable computers, Turing and von Neumann sort of set this thing off. In fact, the architecture that all computers use pretty much these days is the von Neumann architecture. McCulloch and Pitts started off a long, long time ago trying to ask the question, can we use, with the very limited computing resources of the day, can we try to see how we can model how the brain works? And they came up with the very, very first kinds of artificial neural network models, and you will see how they simplified it. This was taken to the next level by Rosenblatt with perceptron, which is basically the precursor to our giant AIs. It was a very, very small thing, but it could play noughts and crosses, as well as one can play noughts and crosses. Yeah? And this is basically, in that case, a 1 or 2 layer neural network. Now we have thousands of layers network. At the same time, there was a contrary stream of thought saying that no, the way to understand, and these guys weren't really trying to understand intelligence, quote unquote, at that time. They had a much more modest goal to try to understand a little bit about how the brain might be doing some kinds of information processing. These guys, Minsky and co., were very keen on having another formal system of understanding computation, or not computation, cognition, and they called what they did AI, and they did this through sort of high-level rules, and this became embodied in a language called Lisp, right? And never the twain shall meet. They hated each other's guts. Okay. So early robotics and problem solving, they actually did show some clever things that you could do with high level, basically rule driven, expert system driven kinds of definitions of AI. And then in the meantime, the neural networks community had been chugging along for years and years. I went to some of the early meetings at NIPS, then it was called NIPS, now it is called the more politically correct NeurIPS. But that same meeting where all the people who did neural network work used to come and present their work. Now it's extremely hard to get into that meeting. So along the way, as neural networks grew bigger and bigger and tackled harder and harder problems, a fundamental issue came up, which is that if you want to represent very long stretches of context, to put it in more familiar terms, if you want to remember what happened a long time ago, something that, or if you're reading a book, right, you have to remember not just what you read in the last sentence, but what happened in the last chapter and what happened at the beginning of the book. You have to keep the context in mind. So this became a really big problem for traditional neural networks, and I expect some of this we'll cover. The first breakthrough on that was through something called, somewhat oddly named, long short-term memories, LSTMs. And then about 8 years ago, this crazy paper came out, All You Need Is Attention. How many of you have heard of this? About half of you have heard of this. This is probably now the most cited paper in history. It came out 8 years ago. All the other highly cited papers in history are for biochemical techniques. Okay, so this was the start of the transformers. Okay, and so this, I'm going to run you through this history, and just to give you some context of where I'm coming from, telling you all the things I'm talking about today. Okay, so these are two of the people who recently got the Nobel Prize for neural networks. I was at Caltech when John Hopfield was still playing around with his ideas, and I got to hear a few of his lectures, and I generally went to sleep in them, but that's okay. I was in the lectures. I imbibed something. Yeah, I didn't get to hear, maybe at the meetings I got to hear from Geoffrey Hinton, but yeah. Anyway, so these guys got the Nobel Prize for this, and we're not going to go down neural network theory at all in that sense. We're going to go down it from a very brain motivated sense, which is what I'll be talking about, and you will get to hear much more of that in the course of this workshop. Okay, so here's another quick glimpse of deep learning through the years, right? So as I said, McCulloch and Pitts invented the neural network in the 1940s. In the 70s, neural networks, so somewhere around here, Rosenblatt did his stuff. In the 50s, he did his little neural networks, toy neural networks, we would call them. And then Minsky and Papert came up with a rather vicious paper in which they proved correctly that with a one-layer network, you could not solve the XOR problem. I won't go into the details of this, but it's a very simple logical operation, and you can't do it. And they made a big deal of this, basically saying that neural networks are no good. What they didn't say, which they knew, they should have said this. What they didn't say was that, yeah, you add a couple more layers, and yes, you can solve it. Okay? And yeah, I'll tell you a bit about that. Anyway, so this was a time when AI, so these guys are the AI guys, yeah, Minsky and Papert. And the neural network guys are the guys they're going after. But backpropagation came along, neural networks got bigger. You get into 3 layers, you got more mathematical ways of describing how neural networks do classification. And then something else happened, something being Google, and generally the internet, which is that two things happened. One is that the amount of data became insane. Google sat on incredible amounts of data, and other big companies could do the same thing. The other thing that happened was that computational capacity grew huge. So Geoffrey Hinton had been working on this for decades and decades, and finally they were able to do stuff with really deep neural networks, which were completely impossible to handle during the years when, for example, I was a grad student. This became possible, and then the era of deep neural networks came up. And deep simply means that there's many layers. And of course, the brain is very deep in terms of the number of layers it has. When I say layers here, I mean logical layers, connectivity layers. And so this is when things started to take off, and you know what has happened since then. That part of it is in your lifetimes. Yeah? Okay, so, and this is an old slide because this says 10 billion parameters. We're already nearly 3 orders of magnitude past that. The field is going really fast. Okay, so there's a sad story here, you know. Minsky and Pappert's paper was so nasty. Well, it could be read in that way. They went after Rosenblatt, and I don't know any of the details of it, but he did commit suicide. Okay, so, and this is what I find really ironical about the whole thing, because now, yeah, in 2025, for the past 10 years, the term AI has been synonymous with neural networks. So I don't know whether the neural networks people co-opted the name AI, or whether the AI people sort of surreptitiously said, okay, no, actually, we were talking about neural networks all along, but now they're treated as the same. But you should remember the historical roots are they hated each other's guts. Okay, so anyway, it's interesting to get these historical pictures of what happened. Okay, just to contrast the two ways of doing things, this is Lisp, and Lisp is like an eruption of brackets. Lisp is the language preferred by the classical AI people. Python, as you probably all know, is the language preferred by people writing AI code these days, neural networks code. PyTorch and all of those tools run in Python. So here I'm doing the same thing. This is the Lisp version, and if you can figure this out, my compliments to you. Yeah, I once tried to learn Lisp and it was extremely traumatic. This is Python. You define the array, you do a simple argument, and you set some of the values to 0, and you've got it. Okay, you know what I like. Okay, so old-fashioned AI, neural network stuff. Okay, all right. So with this, let's now move on a little bit. So artificial networks, the feed-forward kind, they're unrealistic. You know, by unrealistic, I'm speaking from a very brain-centric viewpoint. Yeah, they do not really represent what the brain does. That I think you can all agree, right? They're instructive in the sense that you can learn some of the principles that the brain might be using from them. They're very useful, perhaps too useful, yeah, in that now people are using them for all sorts of shortcuts where they should really be exercising their neural muscle. And the fundamental operation for, at least for the earlier generation, has been classification. Another key thing they can do is learn by example, and that has now been extended to learn by stealing everything there is on the internet. Okay, this is how neural networks get information, and this is very, very different from how you program a computer. You program a computer by saying, do this, put this piece of information in this location in memory. Very, very different from how all of these things learn and how you learn. Yeah, you do not say, put this piece of information in this neuron. Yeah, okay. All right, so this is a very, very brief summation of what these things do. You can do this with feed-forward networks. You've probably all seen a diagram of this kind. The fundamental unit is basically the summation of multiple inputs which are weighted. These weights multiplied by the inputs, the point of input is called a synapse in recognition of their brain origins. And this is sometimes called a neuron, hence it's artificial neuron. But it's a very, very simplified thing. And then you put it through some nonlinearity to get the output. Right? So it's a linear weighted sum of inputs going through some nonlinearity. So this is a fundamental operation in neural network calculations. All very well. And this is the sort of typical neural network. There's a 3-layer network, input layer, output layer, and a hidden layer. And those are lots and lots of synapses. And the fundamental challenge, the fundamental point where the network learns things is to assign values to each of these weights. This is where the memory of a neural network is. When you talk about whether it's a small network or whether it's one of the things that Google and OpenAI have, the secret is in the weights. Yeah? And this is where, for example, if you have an instance of a large language model running on your system, it is through these weights. Okay, so let me give you a fun story of what you can do with these kinds of things. This is a story that was related to me by a fellow student who was doing a sort of a a training program. He was actually from the US military when I was a grad student. And he spoke about so of course the military, what they want to do in life is to shoot things down, right? So what they wanted to do was they wanted to shoot down tanks. And so they made a neural network to do this, and they needed a training set. So they sent out a soldier to take lots of pictures of tanks. All very reasonable, right? You take pictures of what you want to shoot down and you train your neural network. But you also need to now have a training set which includes non-tanks. So they said, aha, we need to also send him out to take pictures of non-tanks. So he went out again and took lots of pictures of things that were not tanks, which is most things in the universe, but yeah. And so finally they had their training set, they put it all together, they trained the neural network, and what does it do? It shot at things indiscriminately. So they went back and they analyzed this data set very, very, very carefully, and lots of mathematics and computation was done. And finally it turned out that the day he had gone out to take pictures of tanks was a cloudy day. And the other days were not cloudy. And so what this classifier was very correctly doing was it was classifying cloudy scenery versus non-cloudy scenery. And it was thinking that's tanks, because that was the training set, right? So this is one of the fundamental risks in training neural networks, one of the flaws in the whole scheme. And it still affects neural networks at very, very high levels. Okay. So that's just to get you warmed up a little bit. Now let's go to a different kind of memory. This is, in fact, the Hopfield network. Yeah. So this is the heteroassociative part. This is the autoassociative part. This is what Hopfield talked about. In contrast to these networks which are feed-forward, in other words, this layer only talks to the next layer, that layer only talks to the next layer. This is a fully interconnected network. Okay? And this has some, but note, this one also has a bunch of synapses, and this is also where the memory is in these networks, in these synapses. So there's a lot of interesting things that come out of Hopfield networks. This is partly why his work is so influential. It actually does have some resemblance to what goes on in your brain. It has a learning rule which, unlike the learning rule for feed-forward networks, is biologically plausible. It's called the Hebs rule. Where did I say that? Joint Hebbian synapses. Yeah? So the learning rule is reasonable. And there are various other terms. I won't go into the details of this. Yeah? These all come out of network architecture, and you'll be hearing a lot about network architecture in the coming days. One of the things it can do is pattern recognition and completion. So supposing you have a couple of patterns, one face-like pattern and one just the random background stuff, you can give it a partial input, and after a couple of cycles it will regenerate it. This is not terribly surprising to you guys because you're in the age of AI, which is way past this, but at the time this is a remarkable thing. This is something humans do effortlessly. But to see it being done through a very simple connection of neurons and synapses was quite kind of neat. Another interesting thing is it does so by attractors. I won't go into the details, but basically if some random pattern happens to be closer in some kind of high dimensional space to the face than to the random pattern, it will converge to the face, even though this doesn't look like a face. Okay? And anyway, so, but this is nice. This is doing some kinds of things that the brain does. So with this kind of background, I'll now focus on two kinds of networks. One kind of network has to do with synapses, and another kind of network is connectomics, how these synapses are connected together in the brain. Any questions? Please don't hesitate to raise your hand and ask questions. Okay, so let's move on. Yeah, computation within neurons. And let me just start by giving you an overview of the scales, because it's good to have a picture of the numbers, the sizes, the timings. So let's start with the substrate of brain computation. It is neurons. Yeah? And Ramon y Cajal, who some of you know was the originator of the neuron doctrine, he called them the mysterious butterflies of the soul, the beating of whose wings may someday, who knows, clarify the secret of mental life. Well, I hope so. But in any case, these are works of art. He drew them by hand, of course. Yeah? I've actually seen his original drawings in an exhibition. Purkinje neurons, pyramidal neurons, they're all beautiful, they're all very, very distinct, and presumably their shapes, their architectures have something to do with their function. We're still learning about that. So for now, how do we get computation out of these things? So let's now go through scales. So this is your brain. Yeah, as you can see, it's about 1.4, 1.5 liters, about 10, 15 centimeters across. Compared to that, that's the size of a neuron. Neurons are very big cells, by the way. You can see them. They're about a millimeter, human neurons. Okay. We're going to zoom in. This is a model of a neuron. It's a Purkinje neuron. In fact, this is a simulation by one of my colleagues and friends, Eric De Schutter. So this is roughly half a millimeter. And you can see beautiful branching. You can see the cell body. And compared to that, that is roughly the size of the neuropil, one of these bits of dendrite. Yeah, we're going to zoom into that. This is a 5-micron cube, which was the first, perhaps the first connectomics analysis done. A 5-micron cube done by serial EM reconstruction, very, very painstaking work. In this 5-micron cube, there is one, they've highlighted one dendrite in yellow. There's hundreds of axons. One of them is illustrated here in green. And the synapses, again, only a few of them are illustrated here, are indicated in red. Yeah, so this is 5 microns. Now we're going to go down another order of magnitude to the size of one synapse. This is a synapse. This, to be more precise, is just the presynaptic side of a synapse. Inside it, you have the little squiggly things are protein molecules. The little round things are vesicles. The little rod-like things are microtubules. The pink things on top, like a forest, are receptors and surface proteins. And that's the release zone for synaptic transmission. I really want you to get a sense of the sheer complexity of this. Yeah? This is half a micron across. And it is jam-packed with computational elements, otherwise known as proteins. Okay. All right. So here are some numbers. There's roughly 85 billion neurons in your head. There's between 10 to the 14 to 10 to the 15 synapses between those neurons. Each synapse, every single one of those synapses has tens of thousands of reactions going on all the time, probably more. And I'm not talking about individual A meets B. I'm talking about different classes of reactions, different pathways. So this is just sheer numbers. How about electrical events? They're fast. Electrical signal flow is quite fast, millisecond range. Chemical events are millisecond range to thousands of seconds, but to months or days or even years. In fact, if you think about your earliest memories, and if you imagine yourself as ancient as me, yeah, those memories are lasting a lifetime. And they are mediated through chemical and structural events. Okay, not through electrical events. Okay. So this is a sort of glimpse of scales, both in size, complexity, and in time. And we've gone through the size scales that I was just talking about. Here's brain versus silicon, right? So we have 1 billion neurons. You already have more transistors in CPUs. This is a scary thought. Yeah. The number of synapses still is larger than what we have in an individual CPU or even an individual transformer model, but it's getting there. You can buy hard disk packs which now have more theoretical capacity than your brain. It's not that you're using everything in the same way that the computer uses it, but you can, again, that I find really scary. Yeah. There are other things. Yeah, there's thousands of reactions in a synapse. There's one signal that a transistor carries. Clock speeds are very, very fast on chips, as you know. The brain does it slowly, and yet the brain does it fast. How does it do this? Yeah, the brain's clock speed, if you like, is very slow, and yet what we do in real time is extremely fast. Okay. All right, and then various other things. Lifetime. Yeah, you guys have lots of lifetime. You're very lucky if your computer is going to be working for 10 years. Yeah. Okay. Anyway, let's move on. Here are a small set of equations. How many of you love equations? How many of you have a nice algebraic equation for breakfast? Yeah? Good. Okay, so you like these. Can you tell me what these sets of equations are about? Come on. Mutter, mutter, mutter. I can hear some muttering, but I can't hear any names. What do these things remind you of? This is chemistry. That's right. Yeah? A plus B gives C. And that's just the same thing in differential form. That's the rate form. Okay, everybody knows that? No. Don't tell me you don't know that. You don't know that? Yes, you know that. What's it? Diffusion equation. Yes, it's a diffusion equation. You're so scared of saying this. It is the diffusion equation, of course. Okay, what's this? Nernst equation. Good. Now we're starting to get a little bit warmed up. What's this one? Ooh, they're running down again now. This is the cable equation. This tells you how signals propagate through a long single dimension cable. These two you probably don't know unless you've taken a neuro course. These are the Hodgkin-Huxley equations. These describe how cells are active. And this is an equation which is commonly used for synaptic transmission. This is cool. Yeah? 7, 8 equations. This small set of equations describes almost all of the phenomenology, a great deal of almost everything that we know about brain computation. Yeah? There's of course huge amounts more detail that goes into it, but physically principles wise, this is a very substantial component of what there is. Okay, good. So we have a simulator called MOOSE, which we use for modeling across all these scales. I won't belabor it. I'll just say that there are techniques to use these equations and figure out what the brain does based on them. Now, I'm seriously over time, but I'll try my best to wrap up. I'm still in the intro, you see. I know. It's okay. Here's a very cool simulation that was done a few years ago, or a study that was done, which asked how large a neural network do you need to represent one neuron? Okay, so first of all, this is the neuron they were modeling, and they ended up doing a neural network with 7 layers, 128 features per layer, a history of 153 milliseconds. In other words, a fairly substantial neural network, and it does a reasonable job. So the cyan trace is from this system, and the magenta trace, sort of in dotted lines, is the neural network. So it misses some action potentials, but it follows the subthreshold activity pretty well. Yeah? So this is not too bad, but it took a large neural network to do what one neuron did.
What does it mean for if you have a 153?
That means that in order to figure out what's going to come next, you have to know what the input was up to 153 milliseconds earlier. Okay, now this would not work if you included the chemistry, because the chemistry goes on for hours, days. Yeah, so this thing only works for a neuron which has non-plastic synapses. In other words, a pretty useless neuron which doesn't remember anything. Okay, and it still took that kind of neural network. Okay, so this sort of gives you at least the beginning of a picture of one reason why brain computation is extremely efficient. It can do an awful lot in very simple biophysics. And it takes a lot of, or to put it another way, neural networks are grossly inefficient. Okay, information as chemistry. If you think about it, question? What?
Is it right to say that the neural network should model those fine details?
Yes.
Does it really make a difference in the...
Yes. It makes a difference because the fine details are how the neuron keeps track of when to cross this threshold. Yeah? The fine details are due to the cumulative sum of the tens of thousands of inputs it is getting. And although at any given instant, most of those inputs are not crucial, but their sum, whether they cross the threshold, is crucial. Yeah? We'll also see in a little bit that it's not just their sum, it's their organization in space that is also crucial. Yeah? So the neural network needs to model all of these things in order to get it right. Okay. Okay, so information is chemistry. So this is a straightforward enough thing. For a computer or for a neuron, the way you think of it, information is represented as voltage. When we talk about chemistry, it's represented by the identity of the chemical signal, and then of course its amplitude. And there are thousands and thousands of different chemicals. Yeah, and we haven't even started to talk about spatial separation, which it turns out that chemistry is much more compact than electrical signaling. Chemical signaling happens on the length scale of microns, and therefore you can subdivide a cell into tens of thousands of parts, each of which is doing its own thing in parallel, compared to electrical signaling where there's length scale is of the order of hundreds of microns. So here's an example of a logic operation. It's an AND gate done by molecules. On the presynaptic side, you have neurotransmitter release. Some of you know this from school. Most of you know this from school. And on the postsynaptic side, you have a very interesting receptor called the NMDA receptor. And this is interesting because it has a magnesium ion sitting on its pore, and magnesium is positively charged, and the current you want to go through it is also positively charged. And so what happens is this plugs it. It plugs it unless the cell is the postsynaptic cell is already somewhat active. In other words, this channel will only send in information when you have activity both here and here. It is a logical AND gate doing the operation of association, and it's doing at the level of individual molecules. Okay, so that's one example of a chemical computation. This is something I worked on for my postdoc. This is a very, very small subset of what we now know about the chemical networks in the synapses. There's hundreds, thousands of these things going on at the same time. These are important in plasticity, learning and memory. This is what it looked like on my computer many, many years ago. It's a mess, right? Yeah, I like it very much. It's my kind of mess. And it's because of this complexity that these networks are able to do so much. Yeah, and this is still a very, very small glimpse of what you have over here. So let's just do a little exercise. Can you spot the feedback loops? Pointed to one over there. Very good. Any others? There's a big one over here. Very good. Any others? Where? Very good, very good. Any others? There's an interesting negative feedback loop here. Yeah? The little plungers are negative, the arrows are positive. Okay, so look, there's lots of feedback loops in here. How many of you have studied dynamical systems theory? You got some idea what feedback loops do to you? They make your life miserable, right? Yeah, they lead to all sorts of nasty math. One of the things they do is they lead to a phenomenon called bistability. If the feedback loop and numbers are just right, and bistability simply means that you have a system with two stable states. You can think of them as energy minima. And if you're in one state, think of the marble moving back and forth. It is going to stay there unless you push it really hard across an unstable state, and it will go to the other state. This is in fact the basis for many kinds of computer memory, a bistable system. And you can implement it through these feedback loops in chemical signaling. This is what I did as a postdoc. Yeah. And the reason why this is important is that if you have, let's say, this very, very idealized feedback loop over here made of molecules, and you give it a strong stimulus, it becomes an active feedback loop where A turns on B and B turns on A. And it stays that way even if the molecules turn over, right? And so you can store information through chemical activity in a feedback loop. And this is important because this ability to store information at a synaptic level is crucial for memory. And I'm going to illustrate this through this cartoon picture of Pavlov's dog. Everybody knows about Pavlov's dog? Yeah, Pavlovian conditioning? Okay, good. So here's Pavlov's dog. Pavlov's dog gets food. Yeah, this dog is an unfortunate animal. It has only 3 neurons. Yeah, it's got one neuron, which is the food neuron, and when it detects the food, it produces saliva. Okay. It's got a light neuron, which is the lights turning on, but it's not correlated with the food in any way. The lights go on and off, but there's no correlation. What about the bell? Everybody remember what the bell did? What did the bell do? That's right. They rang the bell before the food was going to be delivered. And so that is what's called an association. We saw an association about 3 slides ago. What was that? It was the molecular AND gate, right? That is, you have the input and the output neuron both being active at the same time. So you have the association between the bell and the food. So now you get an AND gate, you signal a trigger, and then you feed this trigger through the magic of chemical signaling. You feed this into one of those feedback loops, and you can change state so that now the synapse is a strong synapse. You have amplified the response, you've stored it in a feedback loop, and now your synapse, which was initially weak, becomes a strong synapse. And it stays that way because it's bistable. Okay? So now the bell signal comes along, it sees a strong synapse, and it turns on the food neuron, which causes it to salivate. Okay? So at this level of a 3-neuron dog, we have learnt Pavlovian conditioning. And the point of this is of course a very cartoonized version of what's happening, but we have been able to go from molecules to a behavior of an animal, yeah, to a learning phenomenon in an animal through changes in synaptic weight. Yeah, and the changes are mediated through chemical signals. Okay, so this is one level of network that I'm telling you about. At the level of chemical signals, at the level of all of this stuff, information is flowing, and this too is a network which is doing something important. Okay, now I'm going to change gears. I'm going to talk about networks between cells. This is basically the problem of connectomics, and I think this is closer to Sutabro's heart. And I'm going to present you with a very, very specific problem about wiring in the brain, which you may not have thought about. So the problem, I'll start out by stating the problem, and then I'll talk about a little bit to give you a little bit of background, some of the spatial computation that neurons do, and then I'll talk about the problem of wiring and that of noise. So here you've seen this quote before from Ramon Cajal, and this is the starting point for this analysis of wiring cost. We have 85 billion neurons. Okay, I already told you this. We have somewhere in the region of 10 to the 14, 10 to the 15 connections between them. How do you specify these connections? That is the fundamental problem. You have only 25,000 genes. Yeah, this is a much smaller number than that number. In fact, most of these genes are used basically for keeping you alive. Yeah, they're not assigned to setting up the wiring. So how is it possible to set up that many connections using that many genes? Has this problem ever occurred to you? Definitely not. Yeah, if it's occurred to you, I really want to talk to you. Yeah, we're doing admissions. I want to talk to you. Yeah. Okay, so where's the information coming from to wire up that many synapses when that is the total amount of information in your genome? Okay, so there's several ideas. One is that instead of wiring it one-to-one, point-to-point, you don't have to specify every single connection individually. Instead, you say this bundle of axons, this group of cells are connecting to that group of cells. You can sort of do that through molecular gradients and so on. I won't go into the details. What else can you do? You can use the geometry of the growth. That is, as the brain forms, cells are close to each other at certain times, and then they get further apart. But once you form the connections, the axons can simply get longer. Yeah? So that's another way to use sort of incidental information during development as a wiring rule. Okay? Yet another one, which is perhaps I think the crucial one, which is you use the information from the world. You train the network to set up those connections. And that is almost certainly where most of the information in your brain comes from, through experience. Okay? It's not through the genes, it's not through pre-wiring, it is through signals you get ever since you were an infant till now, and you keep refining these connections. So that's where these weights come from. But we thought of another way, yeah, which is that maybe you don't need to go to all the trouble to specifically set weights and connections for every single synapse. And so I'll talk a little bit about a project we did using statistics and random connectivity as a mechanism for doing this wiring. Okay, so let's give you a little bit of a motivation for this. These are actual experiments. Yeah, this is an image of a neuron from monkey visual cortex. And when you give it a certain kinds of stimulus, in this case, a set of horizontal bars, you see certain spots on the dendrites of the cell are active. When you give it a different orientation, you see a different set of spots. Yeah? When you give it other fatter bars, you get different spots. When you give it different colors, you get different spots. Question? What I mean, no, this is the inputs coming into the dendrite. Okay. And the point I'm making is that inputs are not coming in at random. Inputs for a certain feature are coming in very well-defined spots. Yeah? And these aren't spots of one input. They're spots of tens of inputs coming in at the same location. So this sort of really hammers home the question, how does the brain wire things up so that not only are the cells connected appropriately, but subregions within the cell are connected such that related inputs are coming in to the same spot, to the same zone on the dendrite. Okay? So this is one of the problems we set out to analyze. Yeah? And one of the other interesting things that the brain does, I'll just explain in a moment, is that these signals do not only come in a small region, sometimes they come in a very specific order. And if they come in a specific order, there are chemical mechanisms in the dendrite which can allow for selective amplification. So if you have sequential input coming in along a small piece of dendrite in blue, you get a large response, whereas if you have exactly the same set of inputs but in a random order, you get a small response, and that is in red. Okay? So this is very simple reaction diffusion chemistry. Okay? So the point of this is, so you can see that it's the same inputs, it's just that the ordering is different, right? In the blue input, it starts there, it goes there, it goes there, it goes there, and it goes there. It builds up. In the case of the red one, the inputs are coming in a randomized order. Why is this important? If you had, so it's in the same kind of zone as this, but it's saying that not only is the proximity of the inputs important, the order in which they come in is also important. And this is relevant because a huge amount of information in the brain is sequential, it is timing. And to have things come in a specific order gives you additional information about the stimulus. So these are processes that go on in the dendrite regardless. Okay, so how can we wire up the brain to use these kinds of computations? So this is work that my student now, Dr. Bhanupriya Somashekar, has worked on. And the idea is the following. Yeah? If you just talk about grouped inputs, don't worry about the timing. These will come all together. If you talk about timing, you have a certain sequence in time, this being the time axis, this being the axis of groups of inputs. And this is random connectivity to some output cells. So the idea is that even if you have random connectivity and you apply a certain sequence of inputs or a certain grouping of inputs, you will have a few cells which will be connected up. And our job is to estimate the statistics, the likelihood of this. Yeah? Okay, so what we're going to do is we're going to home in on a neuron which gets these inputs, this set of inputs, color-coded, all coming close to each other on a small piece of dendrite. Okay, just to give you an idea of length of time scales, electrical signaling is long time scales, hundreds of microns, and of the order of a millisecond. This is one kind of chemical signal involving calcium. This is about 10 microns and hundreds of milliseconds. We won't go into details. And there's yet another slower kind of chemical signaling, which is same length scale but even slower. Okay, so I won't talk about the different regions of the brain and the probability of connections. Just suffice it to say these are numbers that go into the statistics. So the idea then is that if you have different events which are contributing to the computation, you want to do something like an AND gate to say that all of these inputs have to be present in a certain location at a certain time. How can you do this? Or not so much how you can do this. We know the neuron can do this. How can you set up the connections to do this? Okay, and there are different kinds of groups. You could have all of them distinct, or you can have some overlapping, or you can have all of them the same. I won't go into the details. These are all cases that we analyze in the statistics. So for those of you who like your math, so expected number of connections from any neuron in a particular ensemble to arrive anywhere on the target cell is simply the probability, connection probability, times the number of neurons. Okay, this is a nice easy place to start. Okay, expected number of inputs from any neuron in that ensemble in a small zone of length z on a target cell is because of course you could have the zone anywhere on the target cell, is Pn z by L, and that gives you the expected number of inputs. So the probability of the zone length receiving one or more inputs from a particular ensemble. Now we're saying that not only does it get that input, it also gets multiple inputs which are relevant, and that is approximately 1 e to the minus nu. And then if you want to get more inputs from each one of those ensembles, you have to take another power of m, and probability of that going anywhere on the cell is that, roughly speaking. Okay, so I'm not going to ask you to derive this, but the point is this is very back of the envelope calculation. This is the simplest of the calculations she did. There's several pages of other things, and if you want you can look at all the lovely equations in her paper. Yeah, so this just sort of illustrates how we go about doing the statistics, the probability of the connectivity. Okay, and here's a schematic of the neuron. So there's our neuron. We sort of treat it as a long single dendrite in the cell body, and these are the little lollipops are the spines where the connections happen, and Z is the zone length where you get multiple inputs. Okay, so now working out how you can possibly get the appropriate convergence. Okay, so it turns out that you can get 3 to 4 inputs. It's quite likely that you'll get them, and we did this both through math and through simulations to estimate the numbers. And this is the size, this is the number of inputs that have to converge, and this is the probability that you get that convergence, ranging from 10% to quite a small probability. And of course, if you're down here, you won't see any examples of this. Yeah, if the probability of such connections is very, very low, you won't see it at all in the network. If the probability of connections is very, very high, that's also pretty useless because all the neurons will be doing the same thing. The interesting case is in this middle range where a small fraction of the neurons are responding to one set of inputs, a different fraction of neurons will then respond to a different set of inputs, and so on. So this is the range where we have interesting computations happening. We're just doing a standard feed forward projection. We'll come to the problem of noise in a little bit. Yeah, activity and noise in a little bit. This is just saying, are the connections present? We're not asking about activity. Yeah. So you can get these inputs. They're pretty likely. Given the total number of cells, which is of the order of 10 to the 5, 10 to the 6, you're definitely going to get a decent smattering of cells which receive this kind of connection. You can have other variants. You can say how many of them are going to be active at any given time, given the known rates of activity. And that's a very similar kind of chart. And a similar region of space is useful for computation. Okay, so now we've done this. What we find is that random connectivity supports this wiring. In other words, even with just random connectivity, you are going to get a decent number of connections which obey the rules that you want for grouped input. Yeah, and I will leave it as an exercise for the reader to figure out how you do this for sequential inputs. It's just more similar kinds of calculations, except now that you have to stipulate that the inputs come in a certain order in time and space, time and space. Okay, now we go to another problem. Wait, there's a question? No? Which is that of noise, which is the problem is that if you have noise, you can get spurious responses. You can get it because the whole set is active through noise, or you can get it because some of these happen to be active because of noise but not because of a genuine input, and this can cause all sorts of problems, and so we had to assess how big this was. Again, lots of math went in, lots of simulations went in. I'm breezing over all of that, and this says that I'm nearly done with my time. So what we find basically is that if you have strong nonlinearities in the neuronal response, you can resolve the noise. So this is what it would look like if you had a weak nonlinearity. The neuron output is complete garbage. However, if you have a strong nonlinearity, then you get very, very clear peaks which distinguish your stimulus driven from the non-stimulus driven input. In other words, you can resolve the signals over and above the noise if you have strong nonlinearities in this system. And anyway, this is another way of saying it, looking at the statistics of the population with weak nonlinearities, where the random stuff is in purple, the stimulus driven stuff is in blue, and you can see that there's a strong group of cells out there which are far away from the random activity set. Unfortunately, if you have fully mixed groups, you cannot resolve them. This is one of the categories of groups. So it means that there's a limitation to this kind of connectivity in terms of what you can resolve. So to cut a very long story short, since I can see many of you are in need of your coffee, the result is that strong nonlinearities make it possible for neurons to detect inputs that come in small groups, even if there's lots of noise in the system. And noise is just random activity of all of the others, tens of thousands of inputs coming to each cell. Yeah? And there's another exercise to the reader if you wish, or you can go and look at the paper. It turns out that sequential inputs are actually not possible to resolve even with the strong nonlinearities at the cell body level. But if you look at the local regions of the dendrite where the interesting signaling is happening, then then you can actually resolve the fact that there's a sequential input present there. Okay, so these were the findings from this.
So okay, I understand that the nonlinearity is actually reducing the number of false positives. What are the false negatives? For example, all the detect signals when it shows.
So yeah, so we analyzed all of that. This kind of indicates where you are, you see. If you exclude the ones which are on this side of the peak, these will be the false negatives. Yeah, because you've just said that I'm not going to include anything down here. Yeah, so but it's not bad. I think something like 70-80% of them are correctly classified. But here it totally fails. Okay, so yeah, so sequential activity is hard to resolve, but it can be resolved at a subcellular level. Grouped activity, where you just have clustered input coming in, that can be resolved. So the point of this is that we've been able to come up with another way of saying, how do you wire all of these things together? Yeah, how do you wire all the neurons together without having to have predefined rules that connect one point to another? And it turns out that random projections are a good enough way to at least get started on this. So let's put these things together. So just to remind you, these are some typical numbers for the brain. And if you were to put these two things together, the networks that I spoke about first, which give you memory, the subcellular networks, with the connectome level networks, space we discussed is submicron to long distances. Time we discussed is long term versus short term. Metabolic cost, it turns out, is very, very small for the chemical signals, as opposed to much higher costs for long range electrical signals. Parallelization is extremely high here. Every single synapse has got masses of parallel processing, and there's 10 to the 14 of those synapses. There's a lot of parallelism in the brain. When people talk about parallelism, they're actually talking about this much more modest kind of parallelism, which is the electrical signal parallelism between neurons. but it's modest compared to that. And who trains who? Well, the chemical processes are trained by the inputs from the connectome, yeah, and the local activity, which is why it's so important to know how inputs converge. And the connectome is trained by A, inputs from the world, and B, how the network forms. The network is formed through chemical activity, and the synaptic weights are stored through chemical activity. So it's very much an interplay between electrical and chemical domains to set this up. And so that's why I've sort of overlaid the chemical on top of the brain, which coincidentally look a little bit the same. Okay, so this is what I've done. I gave you a bit of history. I talked about networks within cells, how you can store information at very, very small scales. And that's not the only thing you can do. You can do a lot of other processing. I focused on memory. I spoke about networks and connectomics and how you can look at the very large scale and then how these things do actually come together. I'll leave you with some thoughts. Yeah, the brain does not partition between electrical and chemical signaling when it's doing computation. It works seamlessly across these scales. The brain is extremely efficient at learning. It learns very fast. How many of you have ever trained a neural network? Yeah? How many cycles of iteration did you have to do? 10.
10 epochs.
10 epochs. How many groups within each epoch?
Based on the data set.
Yeah. So typically you have to do tens of thousands of total training runs, right, before you can train it on anything. Yeah. Humans don't have that luxury to do that. Yeah. And the important thing is, what I've spoken about here, is that the very small and the very large networks coexist seamlessly and complement each other to achieve this. So let me leave you with this thought. Yeah, GPT-4 has 1.8 trillion parameters. Yeah, 1.8 into 10 to the power of 12. It occupies racks and racks like this. It consumes the power of a nuclear reactor to keep these things running. This is your brain. Yeah, it's 1.4 kilograms. It consumes 20 watts. It has even more synapses still than the largest GPT in the world, and it does this all within your head. Okay, so use it. Don't let the AIs take over what you're doing. Okay, on that thought, thank you very much. Any other questions?
Mentioned that not all the information about connectivity would be encoded in the gene.
Very little is encoded in the
You
gene.
mentioned 3 ways in which you can encode. So environment, can you give some example? Is there any?
Every bit of sensory input you get is going to feed into brain activity and therefore can potentially increase or decrease weights. But it's even more than that. Even before you're born, there are structured waves of activity going, for example, in your retina. And these waves of activity are used by the developing nervous system to wire up your visual cortex in a certain manner, in a spatially coherent manner. So again, it is signals, it is activity that is driving the wiring of the brain. Not just the strength of connections, but actually the very fundamental wiring. Once you're born, you have a huge amount of, you have far more connections than you have when you're an adult. And you start losing those connections based on inputs you get, based on correlations between sensory inputs you get. So this is all ways in which the world programs your brain.
What we're selecting the wiring for is more convergent.
Yeah, so that's a good point. But you know, the world is the same for, in a broad statistical sense, it's the same for everybody. Yeah, you have certain features in your visual environment. You hear certain ranges of sounds. You have certain tactile. I mean, all of these are statistically they're broadly similar. And the same way, brains are statistically broadly similarly wired up. The details of what you remember and what someone else remembers are down to specific experiences, but the broad statistics of what you've experienced through your life is common. And so that's why the broad wiring is very similar.
What does it mean by this non-linearity?
Good point. Yeah, I did not expand on that. So one of the most important nonlinearities in the standard neuronal function, which most people talk about, is the action potential, right? You cross a certain threshold, and then suddenly it's an all or none event. That's very, very nonlinear. In the chemical domain, I very briefly touched upon these bistable switches. So bistables are extremely nonlinear things. Yeah, you cross a certain threshold, they flip to one state. You go the other way, they flip to another one. And there are many other nonlinearities. It's just full of them. But these are the kinds of nonlinearities that one sees, for example, in the specific case of the signal flow from the neuron. There are these ion channels, the same ones that cause action potentials. So they're sort of low action potentials that amplify the signals coming in from the dendrite to the soma. And that's also a very strong nonlinearity.
So in this model, that nonlinearity with nonlinearity means some action potential.
So we modeled it in a much more abstract way because these were big calculations. But it's basically how steep is the activation curve. Yeah, that's all we did.
We still have time for a couple more questions.
You mentioned that memory does not have electrical signaling, it's mostly chemical, but through sensory perceptions you do learn, and these are electrical connections. So are they getting further into the
Yeah, so that's what I said, that you inputs from the connectome, in other words, the inputs that come into the cell are what instruct synapses to get stronger or weaker, right? So that is where the linkage is. And then once the synapse is stronger or weaker, it tells that signal, that synapse to be strong, which means that the electrical signal passes more or less effectively. So it is a bidirectional thing.
You were able to resolve sequential signals.
Can you speak up?
You were able to resolve sequential signals in the subcellular level, but it was not possible at the level of the cell. What is like the fundamental difference in that? What enables this?
So the thing is, at the subcellular level, you're just dealing with a few inputs coming in. Yeah, there are a few extra inputs which will cause noise, but if you're looking at it at the cell body, there's 10 to 30,000 other inputs that are coming in, and you want to resolve this little bit over everything else. Yeah, so here you can do it, but here if you're summing everything, you can't do it.
So in one of the slides you showed that there is localized activity on the dendrites based on the input. How is that localization maintained?
It's a very simple outcome of diffusion length. So you have, let's say you have a uniform distribution of molecules, yeah, and through some chemical signaling, some of them become active locally, and then they propagate, the activity propagates a certain length. It will propagate basically by the length constant of diffusion, which is about a micron. Okay, so and then there are further elaborations that you have these structures, this dendritic spines are actually diffusion limited compartments. So basically diffusion is the answer. It keeps it short range.
Sir, I have a little bit of a different question. So throughout your talk, I could see that there's an undercurrent about ethics. Some firm beliefs that you have about doing the right thing in terms of academic credit, or about copyright laws, or about power consumption.
Yeah.
There are some very real ways that they are trying to tackle some very limits to overcome, either about power, the density of the transistor. The latest one is 2 nanometers, but it may further become much more denser, or about the how to make it more compact, or accessible. Perhaps not this century, maybe the next, but it could be.
Well, great things are going to happen in a couple of years.
Could be widely accessible. How do you see, if at all, that there's this perfect replica of a brain?
Yes, yes. Well, see, you don't need the perfect replica of the brain to get into really difficult moral territory. We're already there. Yeah? I mean, how many of you have used, for example, one of the deep research tools that Gemini or OpenAI provides? Have you used those? If you haven't, you should try it out. It is a very sobering experience, right? In 5 minutes, it will give you a summary at the PhD level of the literature in a very specific topic. And it will do so by actually going and looking up that literature. So to me, that is the fundamental. I mean, these other things, environment and all, are very important. The fact that they've stolen all of human creativity and put it into these AIs and are charging us for it, that is a big problem. But the real problem, I think, is that of what do humans do when there's a whole bunch of machines which are smart in certain ways in certain domains, and those domains keep expanding. Yeah. So for you guys, you know, you have no choice. You are in this world which we older people have made for you. You're in a world where you are competing against machines in an intellectual sense, and you have to do what humans and brains are designed to do, which is to learn fast, adapt well, and make use of these tools. Because if you imagine that you can just go and turn the handle, a machine can do it better. And that's, yeah, I mean, you can talk over that over many, many weeks. It's a long, long topic about the morality and the ethical issues in that. I teach a course called AI for Good and Evil, where we discuss some of these things.
When we say that we have mapped the connectome, for example, C. elegans connectome has been mapped for, like, is the connectome of an elephant should be larger in length rather than a human?
Of course.
So why is a larger brain not? An elephant should have more synapses, should have
Yeah.
more. So why is it not smart?
That's a very good question. Why is it just size that makes for intelligence?
Synapses are larger than of
Yeah. So, well, you're sort of answering yourself. You're saying that just the sheer number of synapses does not equal to intelligence. But we know that already, right? We know that people with different sized brains, there's extremely little correlation between that and intelligence. Yeah. I mean, at a species level, we can say that there's some correlation between human over evolution. But you know that Neanderthals had much larger brains than humans. Yeah. Okay. So much for that correlation. Okay.
So I guess any further questions we can talk about. So let's just thank you for a very fantastic.
Thank you.